Hi, DDTJ and welcome back to my new video. Today I have a new idea and I found it is quite interesting, but I still haven't got a chance to test it on a real machine, but I hope I can do it later. And the video today I'm gonna talk about a new way, a new method to rough cutting a screw shaft. Yeah, you can see what I mean. A screw shaft is something like this. It's like a conveyor screw or something. A screw shaft with a very fine pitch compared to the shaft diameter, like this one on the screen you can see. And here's some information about the part. The the measure diameter of the screw is about 60 millimeter, and the pitch is 6 millimeter, and you can see the width of the groove here is about 4 millimeters. So we got 2 millimeter thickness of this fins. Okay, and with the part like this, I used to rough cutting with a rotary toolpath and using a flat end mill, a flat cutter like this, very small end mill for roughing the part. I use a rotary toolpath like a project curve or a swap milling or something like this, and I rough it with a flat end mill, and I realize it's pretty slow. It takes a lot of time to rough because you can see we use a very small tool to get into the deep groove here, and the cheap uh, extraction is not so good, so you cannot run so fast with this kind of slot. And you can see here I go quite slow, and I use multiple depth of cut in order to rough this slot, rough this screw shaft. And sometimes I got the tool breakage, or yeah, something like this. If I go too fast or the chip, it cannot escape, the tool gonna break and you don't like it, you have to run from the beginning or something like this. And one day I just think about using a bigger tool, another kind of tool, so I can machine it much faster. So I think about the slot cutter, a T-slot cutter, because I got one in the workshop, but I haven't used it for this kind of job. So I think about using a slot cutter. It look like when you do a thread turning, yeah, something like this, a little bit different. You can see there's something special on the screw shaft here. The depth of the groove is quite large, so you need to go quite deep in order to reach the bottom of the shaft here. Yeah, the minor diameter, I call this the minor diameter. And I make some trying, or I do some playing on the part, and I found something pretty nice I want to show you. I have a chance to run this on a real part, and I gonna show you if it's success. If I got some success. Okay, you can see this is the first tool pad I rough with the flat end mill. This is a 3 millimeter flat cutter. Okay, the 3 millimeter, and machine with the rotary tool pad. You can see the project curve. Okay, and it's gonna look like this on the machine. I forgot to tell you, I use 5-axis machine to machine this part. Okay, and when it's go on a machine, it will look like this. I'm gonna show you. Okay, so when I use the 5-axis machine, the part will look like this, and when I use the flat cutter, a 3 millimeter flat cutter, it will cut like this. I will slow it down so you can see. Yeah, this is how it's rough. You can see the A axis is fixed, and only this is the B axis for hash machine. Yeah, and this is the B axis. It's not a C, it's the B axis, because this is the hash machine, so this axis is B is not important. Whatever. But you can see this how it cut, multiple depth of cut, very slow on feed rate. You don't want to go it too fast because it can cause the tool to break. Yeah, this is multiple depth of cut with a flat 10 mil. You can see the total machining time is about 12 minutes. Yeah, this pretty slow, or even slower. This is 1mm depth of cut. You may want to reduce the depth of cut to 0.5 if you get some trouble. So it takes a lot of time, and the tool is easy to break. So I decided to move to another way. I got a slot cutter like this. You can see this is my slot cutter with the diameter of 50mm, and the thickness is 3mm. You can see the thickness is 3mm, and the string diameter is 20. When you look at from the front here, you can see the width of the groove is 4mm. Yeah, from here to here to here is 4mm. So I can use theory. I can use a 3mm thickness tool for going to this groove. Yeah, you can see my idea is will look like this. You can see I use a slot cutter, much richer, and it have a better ability of cheap evacuation. So it's very good for this case if it work. Yeah, and you can see because the thickness of the tool is 3mm and the groove width is 4mm, so that means I can drop this screw with this tool. You can see when I look from the front and the tool go to here, you can see the tool is a little bit too, it's not straight to the Z axis. You can see this is the Z axis, and you can see the tool is a little bit too to the Z axis. You can see I have to tilt the tool because if I go straight, the tool can be golf with the part, because you see this is a helix, and if the tool is not tilted to the helix, it's gonna have some interference when the tool cut into the plate here, so you don't want it. So that's why I have a tilting on the tool like this. You can see this is the tilt angle. Okay, and I will show you how to calculate this tilt angle later. And this is how the T-slot cutter cut into the part. You can see the tool is much bigger, so it's more rigid, and I think it can cut in a higher feed rate, no tool breakage, and better cheap evacuation like this. Yeah, of course you can use multiple depth of cut with this kind of tool. Like this. For example, I use a rough cut with the cutting side offset is 5mm. Okay, and you can see this is the rough cutting. You can see rough cutting, the tool go around and just go outside. It cuts a little bit here, and you can go multiple pass until you get the full depth of the groove. Yeah. So this is how it cut on the machine. I'm gonna show you. Shoo. I think this tool is much better than the flat 10mm, but as I told you, I haven't got a chance to test it on the real part. So if you have a part like this, you can try this way. I think it's quite good. Okay, and this is how I cut it with the T-slot cutter. You can see this is the axis of the machine. The A axis is 2.6. Yeah, it's a little bit too to the front. When I look, yeah, you can see it's a little bit too to the front with a value of 2.6 degree. And I wanna fix the A axis. I just want to rotate the B axis, and this is how it goes. Pew! Okay, you can see this is the rough cutting, the first pass, and the total machining time is just 3 minutes. Yeah, you can go faster with this kind of tool. Maybe you need 2 or 3 passes for roughing. Yeah, I not talk about the machining time, but we have a benefit that the tool is bigger and you can avoid tool breakage with this kind of tool. Very good, cheap evacuation, and you got high cutting speed because the diameter of the tool is quite big. You can see the A value is fixed as 2.6, and it just rotate the B axis like this. Yeah, the tool is fixed at a tilt angle like this, and you just rotate the B axis. It's pretty nice, right? I hope I can run this on my real part. It will be very nice. Yes, it's a little bit similar to the thread turning, but in this case we tilt the tool. We tilt the tool a little bit in order to avoid the interference between the tool and our part. Yes. Okay, so that's the idea for this video, and I'm gonna show you how I create this tool path and how I control the tool axis. Okay, first I'm gonna use a project curve tool path, and you can see here, you can see this surface. I'm gonna use this surface to show you how the tool will go on the part. You can see here the tool is look like perpendicular to, is normal to this surface. This is the surface of the thread of the screw, so the tool is gonna follow this surface. Yeah, sorry, my English is not good, so I cannot describe it clearly, but I want my tool axis normal to this surface. Yeah, I'm gonna create a tool path. Okay, in this case I use project curve. Alright, and I select my slot cutter, and in the projection I'm gonna select the curve here. I want a tool to follow this curve. You can see this is the helix. It's on the minor diameter of our part. Okay, and for example I want to leave 0.2 stock on the part because this is a roughing, and this is the cutting side offset. If you want to if you don't want to use multiple paths, you can leave it yes, 0.1. Okay, so if you leave it 0.1, the tool will follow this curve and just only leave 0.1 stock on the wall here. So okay, there's one thing important, that's the tool axis. Okay, in this case I'm gonna select 5 axis, and for the tool axis control you have many ways to control the tool axis, but this one is very important. You want to select the right method for controlling your tooling axis. In this case I'm gonna select surface. So with this method our tool will stay normal to the tri surface. Okay, we're back to the cut pattern, and you can see we have tri surface here. I'm gonna click on this button to select the tri surface. The tri surface is the surface used to control the tool axis. Normally is the tool will stay normal to the try surface. Okay, I can select this surface. You can see this one, but I don't want to select this because this surface is quite small compared to the tool diameter. So you may got some problem if the surface is quite small. If the center of the tool is not stay on the surface, you may got some problem and the Mastercam will crash. So in this case, I create a new surface like this. Try surface. Yeah, you can see it's the same surface. I just extend the surface to make sure that the center of the tool is can stay on the surface, so Mastercam can do the calculation. Okay, so instead of selecting the small surface, I pick the big one here, right? Okay, so I just select the dry surface for the toolpath, and with this method, tool axis control surface, the tool will stay perpendicular or stay normal to this surface. Alright, and you can select the lead in and lead out for the toolpath. I don't have time to tell you everything here. I just want to show you how we control the tool axis and how it's cut into the part. Okay, and we check the plane, tool plane. It should be top to all plane here. If you see it calculate and it keep calculating, that you do something wrong. It could take forever if you wait. Yeah, I think I have some problem with this toolpath. I need to close the Mastercam and open it again, save it, and use the task manager to kill it. Okay. Here we need to open the Mastercam again and check if we have some problem with the toolpath, and we have to fix it. If you don't fix it, it will calculating forever. Okay, we open the part again. Woohoo! Yes, this one. I need to check the toolpath again to see if we did something wrong. I will hide this surface. Okay, and we go back to the toolpath, checking the cut parameter to see if we have any problem. Do try offset. Okay, cutting side right. Oh, I think I have figured out what happened. You can see here we select this curve for the toolpath, so the tool should stay on the left side of the curve instead of on the right side. So this is may cause the problem. So I'm gonna select left side. Okay, and we done. Pew! Yes. Whoo! It's done. Do. Oh, you can see we have multiple depth cut because in the roughing here I select depth cut, so I can remove it. Now run it again. Yeah, you can see we use this surface level drive. Yeah, we use this surface to control the tool axis direction, so the tool axis will stay perpendicular to this surface. That's why the tool will go like this, and because of this, we can avoid the interference between the tool and the part, because it tilts a little bit like this. Yeah, you can see it's pretty nice, so we can do a rough cutting. You can see in the last try I use a roughing option with multiple depth of cut. For example, I use 3 depth of cut and 1 millimeter or 3 millimeter roughing, 3 depth of cut and 3 millimeter each depth. I'm gonna generate the toolpath again and let's see what happened. You can see this is not what we want, because it calculating the depth cut in this direction, and the tool will hit the part. Yeah, because the depth of cut is calculating using the dry surface, so it will offset normal to the dry surface. That's why you can see we have the multiple depth of cut in this direction, so it will hit the part. I don't want to use depth of cut in this case because it will hit the part, so I don't want to use it. Instead of this, I go back to the cut pattern and I use this value, this option, to control my roughing operation. So instead of using 0.1, I may leave 6 millimeter on the curve here. It's like the wall, the stock to leave on wall in the contour toolpath. You can see now I leave 6 millimeter from here to here, from the fluid of the tool to the wall here is 6 millimeter. So I got my first rough pass, and for the second pass I'm gonna copy another toolpath and I reduce the value of stock to leave on wall here, for example 3 millimeter. Yeah, it's take a little bit of time, but it's work. And you can see with this toolpath I got something like this. This is the first pass and this is the second pass. Yes, it's go in this direction, so it not hit into the part. And you can make another toolpath for leaving, yes, 0.1 for finishing. Okay, so we got 3 toolpaths with 3 different value of stock to leave on the side of the curve, and this will go like this. Yeah, we cut from the outside to inside instead of cutting from the top to the bottom. Okay, and this is gonna work. Okay, now I'm gonna show you. This is my stock. I put the stock in the number 3 level number 3. Okay, and let's see how it cut on the machine. I use 3 different toolpaths for making 3 different depth of cut. Okay, sorry. This is the first cut. Go a little bit faster. You can see it's cut around the part, but let's take a look on this. This is the value of the axis. It's not fixed. You can see it's moving. It's not fixed. That means the axis is yeah, it's not fixed. You can see it's keep running the axis. The B is rotating and the axis is tilting. You can see that the tool axis is not fixed and it's not so good in with this case. Yes, and this is the second pass. You can see it's cut deeper into the part. We had some collision here. Okay, so take a look. Yeah, this called a collision. When it moving from here to here on a simulation, we can see the collision when it move from here to here, but we don't care about it on this video. I just want to show you how we cut this part with the slot cutter. We can take care of the collision later. It's not a problem. Okay, so you can see when I use the tool axis control and use the surface option, you can see the tilting axis is a little bit moved. It's not fixed. So how we can make it fixed? I'm gonna use another way of tool axis control. Okay, instead of using the surface option, I'm gonna select another one. This is the fixed angle to axis. So with this option, we can keep the tilting angle fixed So only the B axis is rotate, the A axis is fixed, and that's, I think this better for this cut. Okay, and on this case the tool will stay 2.6 degree to the Z axis. Okay, I'm gonna make it 0 so you can see the difference. This is 0, that means the tool axis will stay parallel to the Z axis. If you input 0 degree, the tool will look like this. This is the tool axis. You can see it's the parallel to the Z axis. And if you want a fixed tilting angle, so you can input. Yes, you may wonder how I know this value, why is 2.6 not a different value. Okay, I can try 45 degree so you can see it easy. So this is the 45 degree. You can see the tool axis stay an angle of 45 degree related to the Z axis. And when I use 2.6 degree, you can see we got a perfect cut, almost perfect, like this. Yes, you can see the tool follow the groove, follow the pitch. Yes, it follow the helix angle of the part. Very nice. Yes. So how do you know which value you need to input here for the tilting angle? Yeah, it depends on the helix angle of this part. Yeah, of the part you are making. So how we figure out the helix angle of the part? Before I'm gonna show you, I need to do a machine simulation so you can see how it cut now. Okay, so you can see now the A axis is fixed. It is 2.6, and we look from the right side. You can see the A axis is fixed now. Only the B is moving when it's cutting. Yes, and it's much better. You can see the A is fixed and the B is moving. Only the B is moving. Yeah, the X and Y is going a little bit, but I want to keep the A axis fixed. Only the B rotating. It's much better for the tool and the part. Okay, I think so. Let's go like this. Still have collision. Okay, so that's how we control the tool axis with the fixed angle to axis option. Very nice. You can keep the tilting angle fixed, and you just need to rotate the part, and it will do the rest. It's similar to we do a turning, the thread turning operation, but in this case the tool is tilt a little bit, 2.6 degree. So back to the topic, how we figure the helix angle of the part. You can do some hand calculation. Yeah, you have the diameter, because the curve here is stay on the minor diameter of the tool. So there are two ways to figure. I have two ways to figure out the helix angle. Okay, so this is the first way. You don't need to do any calculation. You just do some trick. Go to the transform. You can see this is a helix, and we will roll it onto a flat surface so we can figure out the helix angle. We use the roll function here. I look from the front and I use the roll function. I select the curve here. Choo! Okay, I look from the front, and rotation axis is Y. You can see we have a profile that is roll flat on the flat surface, and you have to input the diameter of the cylinder where the curve is stay on. So I'm back with the part. I have to measure this diameter first. Click on the dynamic. I need to measure this diameter. click on this. So you can see the diameter is about 42 millimeter for diameter. Okay, so we're back with the roll function. Where's the transform, and select rolling, select the curve. Okay, and we input 42 degree. Okay, so you can see the helix now is rolling on a flat surface, and we can easily measure this angle. So this is the angle of the helix of the part. You just measure it, go to angle and click this one. You can see the helix angle is 2.6. yes, about 2.6. so this is how I got the value of the helix angle. Very quick. Come on. Alright, so this is the first way we can calculate the helix angle of the part, and the second way we do some calculation, if you like calculation. Okay, first we measure the diameter of the cylinder where the curve is stay on. Check the diameter. Yeah, you can see the diameter is 42, about 42. So I need to calculate the perimeter of the cylinder by multiply. We use the diameter 42 we multiply with the P. Okay, so this is the perimeter of the cylinder. So if we want to find the helix angle, we just divide the pitch of the screw by the perimeter of the part. So we're gonna take 6 divide by, I just forgot it, I calculated again. Diameter multiplied by P. Okay, 131.88, and we got pick. Yes, and we got this value, so we copy this and we go to Google, or if you have a hand calculator, it's okay. Google. Okay, and I'm gonna put 15 of the value we just calculate. So this is the angle in red, and you copy this value and convert it to degree. Choo! You can see we got the same value, 2.6 degree. Yeah, if you like calculation. Yes. Take a lot of time. Yeah, we divide. First we calculate the perimeter of the cylinder. We multiply the diameter with the P, and after that we divide the pitch of the part by the perimeter. We got a A10, and after we got A10 we can find the angle in rad, and then we convert from the rad to the degree. So we got this value 2.6 degree for the helix angle. Yeah, you can use two way of calculating. Shoo! Yes, that's why I got the value of 2.6. 2.6 is the correct value. Okay, I'm missing the lead out motion, so it's off into the park. you can add the lead out motion. Linking lead in and lead out, you should use lead out at the end of the operation. Okay, like this. Choo. Right. So this is all for today. That's what I'm gonna show you. Another way we can drop a part with the T-slot cutter, and we use the correct tool axis control. We can make a very nice cut, and we can avoid tool breakage because the tool is now bigger and much more rigid. I hope I have a chance to test this method on a real part, and I'm gonna show you. Okay, I hope this helped, and thanks for watching. Goodbye for now.